So today we're starting on chapter 7. We're looking at chemical quantities. This is going to be one of our very mathematical chapters. So we want to be very careful as we proceed with this, take things slowly. Now we're going to see a little bit of chapter 4 in this because that's a chapter we skipped. Really just looking at how to solve problems in chemistry. Now one piece of advice that I have at the start of this is if you are relatively algebraic savvy, a lot of the steps that I'm going to do will seem very slow and very pointless. But I'm tackling the problems piece by piece, step by step, because if you know how to solve the easy problems carefully, you can transition that same skill to solving the more difficult ones. If, however, you just do everything intuitively at the start, you're probably going to be pretty lost when we get to the more difficult material moving forward. So we're going to start by looking at conversion factors, and again, very important, very critical to this whole process. So the idea here is that you can express the same quantity multiple different ways. So for instance, as I show on the screen, $1 is equal to 4 quarters is equal to 10 dimes is equal to 20 nickels. Those are things we know to be true. It's all equal to $1, but we can express it in a variety of different ways. Now, anytime that there are two measurements that are equal, I can create a ratio of those measurements that will equal 1. The way that we can do this, if you're interested mathematically, is imagine the $1 equals 4 quarters. That's my algebraic equation, I could divide both sides by 4 quarters, giving me the ratio of $1 over 4 quarters. And then on the other side, it would be 4 quarters over 4 quarters, which would reduce to 1. So I can take any two equivalencies, put either one on top or either one on bottom, and it will be equal to 1. Now, why is this important? Because you can always multiply something by 1. If you multiply something by 1, you don't change the value, which means I could multiply anything by $1 per 4 quarters without changing the value of what I'm looking at, because I'm actually just multiplying by 1. It's just a fancy looking one. And we call these ratios a conversion factor. And conversion factors are going to be a key aspect to solving chemistry problem-solving problems. So now that we know what a conversion factor is, we can use it in a process called dimensional analysis. And again, one of really the best methods for solving problems in chemistry. Frankly, dimensional analysis, in my opinion, is one of the most useful skills that is widely transferable outside of chemistry. And what we're going to do is we're going to use the units, also called the dimensions. So it's also called unit analysis or unit conversions. And you might have done this in your math classes to some extent. But we're going to use the units that are part of the measurements in the problem to help us solve that. So the units guide the way. So we're going to start with an easy problem, but we're going to be showing every step, all the work. And the work that I show is the work I want to see from you. Now, one of the key things here, again, we're using those conversion factors from the previous slide. And again, anytime we have an equivalency, I can create a ratio where I have the two amounts, one over the other, equal to 1. How do we decide who's on top and who's on bottom? Well, we look at who needs canceling. So we look at the unit that we have, we look at the units we want to get rid of, and we're always going to be cross-canceling. So as I start setting up a problem, if I see a unit on the top that I want to get rid of, I'd better make sure there's a matching unit in a conversion factor on the bottom. And you'll see how this plays out in the next steps. And again, we can create these in long infinite chains because every conversion factor is really just multiplying by 1. So here's the problem we're going to start with. And again, I'm recognizing this has nothing to do with chemistry. This is getting us used to the problem of using the units to help us solve this. So, your school club has sold 600 tickets to a chili supper fundraising event, and you volunteered to make the chili because you're a sucker. You have a very large pot and a chili recipe that serves 10. The recipe calls for 2 teaspoons of chili powder. How much chili powder do you need for 600 servings of chili? So, looking at this, there's various equivalencies that we should be able to identify. we should see that we need 600 servings of chili, just by itself, 600 servings of chili. We see that each recipe serves 10 people. That's an equivalency. One recipe equals 10 people. Also, we see that for every recipe, we need 2 teaspoons of chili powder. That becomes another equivalency. So, again, don't do this in your head. I'm going to walk through it slowly. The skills that we're going to use to solve this one, we're going to use to solve harder problems coming up. So it's going to recap kind of our unknowns. We need to know the number of teaspoons of chili powder. That's our goal. What do we know? Well, we know that we need 600 servings. We know that 10 servings equals 2 teaspoons of chili powder. So we know that. And now we're going to do this. So my recommendation is start your process with what you know that is not a ratio. So look at what's known and find the thing that is not an equivalency. That's where I recommend starting your conversion process. So I'm going to start with that 600 servings of chili that's needed. Then we're going to cancel out the units we don't want by cross-canceling. Top to bottom, bottom to top. Doesn't really matter as long as, well, the units cancel that you don't want. And now we're going to actually do the calculations. So notice I'm starting with the 600 servings here. That's my starting point because that's the piece of information I have that is not an equivalency. Now I look through the information that I have. I look through my equivalencies and I see that I have 2 teaspoons per 10 servings. Notice the way I've set this up. So again, I created a ratio. I'm multiplying it. So again, I'm really multiplying by 1 just in a fancy way. And I've set this up so that that unit of servings will cancel. We know the unit of servings will cancel because we're cross-canceling. I've set it up so we can cross-cancel. I don't want the unit of servings. I want the unit of chili powder. So I'm setting up the ratio so that the units I do not want will cancel out. So we can see the servings cancel. The units we have left over are chili powder. Now to solve this, because that's what I want, teaspoons of chili powder, I multiply all my numbers across the top. 600 by 2 is 1200. I multiply all my numbers across the bottom. It's only 10. Then you divide. Divide top to bottom. 1200 divided by 10 is 120 teaspoons. Now, that's a lot of teaspoons of chili powder. I would not want to have to sit there and count out 1, 2, 3, 120 times. So let's figure out how many cups that would be. That would be easier when making our chili. How many cups would that be? So we're going to need some additional tools. So we're starting this once again. So we ask ourselves, what do we know? Well, we know we need 120 teaspoons of chili powder. We know, because I looked this up, that there are, for every 1 tablespoon, there are 3 teaspoons, and for every 1 cup, there's 16 tablespoons. Now again, this is not something I would expect you to know. This is something, frankly, I look up. And when we start getting into conversion factors for chemistry, they're going to be specific to chemistry, and you will have those as a resource available to you. So that's what we have. So once again, what do we start with? We start with the thing that we know that is not an equivalency. So what would that be? Well, that would be the 120 teaspoons of chili powder. That's our starting point. 120 teaspoons of chili powder. Now I want to get rid of teaspoons of chili powder. So I look at our tools, and I'm going to take one of those ratios there, and I'm going to make one of these ratios, or one of these equivalencies, into a ratio. Which one will I use first? Well, I'm going to use the top one because it has teaspoons. I want to get rid of teaspoons. Now we have to ask ourselves, will the teaspoons go on the top or the bottom of the ratio? Again, we're cross-canceling. Since I want to cancel out the 120 teaspoons, that means the 3 teaspoon part must be on the bottom. So, start with the 120 teaspoons. Notice I have that just over 1. The over 1 is completely up to you. Some people like the one on the bottom, some people don't. It doesn't matter. So 120 teaspoons, so I'm taking that first conversion that there's 1 tablespoon for every 3 teaspoons. And again, the magic of this is that the teaspoons cross-cancel, leaving us with the unit of tablespoons. But we don't want the unit of tablespoons. We want the unit of cups. So again, I move to our tools. Do I have a tool that lets me get rid of tablespoons? And the answer is yes. 1 cup equals 16 tablespoons. So will the tablespoons need to be on the top or the bottom of our next conversion factor? Well, tablespoons is at the top here. Therefore, tablespoons needs to be on the bottom there. And as we see, 1 cup, 16 tablespoons. So again, tablespoons cancels, leaving us with the unit of cups. That's the only unit left, and that's the unit we want, so we know we've done this right. So again, what I do is I multiply across the top, so 120 times 1 times 1. I multiply across the bottom, 1 times 3 times 16. I get 120 on top, 48 on the bottom. Then divide, 2.5 cups. And that is the problem. And one of the nice things about this process is when you're done, if you're actually cross-canceling your units, top to bottom, always top to bottom, or bottom to top, doesn't really matter. If the only unit that's left that's not canceled out is the unit you want, you did it right. Okay, in this slide, just a couple things to point out because the book may be sneaky. 1 cubic centimeter is equal to 1 milliliter. If you've ever watched like a medical show and you have doctors or nurses running around, give this person 20 cc's of something something all stat. CC stands for cubic centimeter, which is the same as a milliliter. Finally, if you mess up your conversion process, and this happens, and it's not your fault, it's not. But let's say the unit you want, instead of being on the top of a ratio, is at the bottom, but everything else is canceled out. Don't panic. Solve it just like normal. Then when you're done, take the inverse or the reciprocal of the answer you get, and that will give you the correct answer. Okay, so now we're talking into 7.1. We're actually into the chapter 7 where we started, and we're going to be talking the mole. Now again, I'm going to kind of work my way around this a little bit, so bear with me, but it's a good journey. So, when we talk about measuring matter, one of the most common ways of measuring matter is to count it. Like, how many apples do you have? Well, I have 5 apples. Well, there you go. You measured it. You can weigh it. You can measure its volume. Some things you can kind of measure multiple ways. So, for instance, when you buy nails, you can either buy nails by mass, or you can buy nails by counting them. Now, there are some units used in referring to a specific number of items. So, for instance, a pair always means 2. A dozen always means 12. And those are things we are just familiar with. That if I say I have a dozen oranges, that you have 12 oranges. Now, some items, again, like fruit, are commonly measured and purchased in multiple ways. So, let's say you go to a fruit stand. It might say that 5 apples are $2. So that means that it's buying it by count. You could go to the grocery store, say it's $1 per pound, you're buying apples per weight. Let's say you go to an orchard, you're buying apples, let's say $9 per bushel, you're buying it by volume. You're buying the same thing, but you're buying it based upon price, based upon different measurements. And that's okay, there's nothing wrong with it. Now we're going to work on extending this idea. So, 1 dozen apples equals 12 apples, because that's what a dozen means. And using average-sized apples, I'm just kind of making this up, let's say a dozen apples is about 2 kilograms. That's okay. Also using average-sized apples, 1 dozen apples is about 0.2 bushels. Just take my word for it. Now again, notice what I've created. I've created equivalencies. 1 dozen is equivalent to 12 apples. 1 dozen is equivalent to 2 kilograms. 1 dozen is equivalent to 0.2 bushels. It's all based on the amount of a dozen. That's a common unit that they all have, and it's an equivalency. And what can I do with an equivalency? I can create the ratios that are equal to 1. Very important. And now for using this with unit conversions. So let's say I want to know the mass of 90 average-sized apples. The mass of 90 average-sized apples. Well, first off, what's our unknown? What are we solving for? Well, I want to know the mass of the apples. What do we know? Well, I know that we have 90 apples. I know that a dozen apples equals 2 kilograms. And I know that a dozen apples equals 12 apples. That's information we know. With this, we can actually proceed with the problem. So, you can ignore this bottom piece. Notice I start with what is not an equivalency. I start with the 90 apples. Now I want to cancel out the apples, so 90 apples, that's the amount of apples, so I'm looking for a conversion factor that's dealing with the number of apples. Oh, that there's 1 dozen apples per 12 apples, and the number of apples cross cancels. Now, every time you cross cancel something, it should give you a nice feeling, like rubbing a kitty's tummy. So I've canceled out that, so I'm now in the unit of a dozen apples. Well, I don't want a dozen apples, I want massive apples. So I look at my tools and I say, oh, for every dozen apples, it's 2 kilograms of apples. So for every dozen apples cancel, it's 2 kilograms of apples. So the only unit that's remaining is kilograms of apples. So I can now multiply across the top. 90 times 1 times 2 is 180. Divide by 12 times 1, which is 12. 180 divided by 12 is 15. This is the same process we used with the chili, but now we are bringing in amounts and masses and the word dozen. You've done it before, same exact process. Now this leads us to the mole. The mole is an amount, just like a dozen is an amount. When we say that you have a dozen of something, that means you have 12. It doesn't matter what it is. But we use the mole specifically for counting atoms and molecules. Because they're so small, talking about molecules or anything in terms of like a dozen was impractical because it's almost no matter. So 1 mole represents 6.02 times 10 to the 23rd of anything. This is a very, very, very important factor to know. 1 mole equals 6.02 times 10 to the 23rd of anything. Just like 1 dozen equals 12 of anything. A mole is just like a dozen, but way, way, way bigger. So a mole of hydrogen molecules would be 6.02 times 10 to the 23rd hydrogen molecules. A mole of cars would be 6.02 times 10 to the 23rd cars. A mole of moles would be 6.02 times 10 to the 23rd moles. Again, a mole just means 6.02 times 10 to the 23rd of anything. And this is a amazingly, astoundingly large number. How big of a number is this? So if you had a mole of chicken eggs, a mole of chicken eggs would fill the world's oceans 30 million times. It would take 10 billion chickens laying 10 eggs per day, more than 10 billion years to lay a mole of eggs. And then one of my fun ones is a mole of seconds would be 1.9 times 10 to the 16th years. So again, that's about 1.35 million times longer than the age of the universe. So there's not even been a mole of seconds in the existence of the universe. A mole is an astoundingly large number. But it's a number, and it's really useful for counting, again, like atoms and molecules and whatnot, because they're so small. So we call 6.02 times 10 to the 23rd Avogadro's number in honor of Amadeo Avogadro de Cuenca. He laid the groundwork for it. He didn't actually discover this or come up with it, but he laid the groundwork for it. Now, when dealing with units in chemistry, you often want to think about what you're actually talking about. So if you say you have a mole of oxygen, you have to remember, oxygen is naturally a diatomic molecule. So a mole of oxygen actually is saying that you have 6.02 times 10 to the 23rd oxygen molecules, not atoms. A mole of iron is 6.02 times 10 to the 23rd atoms of iron. Iron is not diatomic. A mole of salt is 6.02 times 10 to the 23rd formula units of salt, sodium chloride, because it's an ionic compound, so its smallest unit is a formula unit. So let's look at how we tackle problem solving with this. Handled just like the example with a dozen, which is why I kept saying a mole is like a dozen. So how many moles of magnesium are in 3.01 times 10 to the 22nd atoms of magnesium? So how many moles would that be? Well, we have our base number, 3.01 times 10 to the 22nd atoms of magnesium. That is not an equivalency, that is a number given to us, so we're going to start our conversion with that. Now we look through the information we have and we go, oh, 1 mole of magnesium is 6.02 times 10 to the 23rd atoms of magnesium. we have our equivalency. What can we do with an equivalency? We can make it into a ratio. So 3.01 times 10 to the 22nd atoms of magnesium. Again, this is what we start with because that's the number we have that is not an equivalency. I then use that there are 6.02 times 10 to the 23rd atoms of magnesium to equal 1 mole of magnesium. Notice atoms of magnesium cancel because I've set it up to cross-cancel, leaving me with moles. I want moles of magnesium. That's the unit I want. So I'm good. So I just multiply across the top, 3.01 times 10 to the 22nd times 1, divided by 6.02 times 10 to the 23rd, gives me 5.00 times 10 to the -2 moles of magnesium. Now, one thing I want to stress here. Notice here with moles of magnesium and moles of magnesium, I abbreviated mole MOL. That is the official abbreviation for moles. It's not a great one. It just saves you one letter, but that is the official abbreviation of a mole. So just keep that in mind. Now, as a note, Avogadro's number is a conversion factor. Treat it as a set value. Don't worry about Avogadro's number in terms of significant digits. Okay, so now we're going to branch off a little bit. So the mass of a mole. So if you look at the atomic mass on the periodic table, that number was designed so that it is also the mass of 1 mole of that element. And we call that the molar mass. So for instance, an oxygen molecule, each oxygen atom has an atomic mass of 16 grams. Oxygen is diatomic. 16 plus 16 is 32. So we said oxygen has a molar mass of 32 grams, or that there are 32 grams of oxygen for every 1 mole of oxygen. And again, if you have a compound, the molar mass of the compound is just the sum of the masses that make it up. Pretty straightforward. So for example, carbon dioxide here has a molar mass equal to the sum of the molar mass of 1 carbon, which is 12, and 2 oxygens, which would be 32. 12 plus 32 is 44. So carbon dioxide has a molar mass of 44 grams, or we could say that 1 mole of carbon dioxide has a mass of 44 grams. Now your book does something a little funky. They use a variety of terms, so they'll use the gram formula mass, or GFM, gram molecular mass, GMM, gram atomic mass, GAM. They're all molar mass. Gram formula mass is specific for ionic compounds, molecular mass is for molecular compounds, atomic mass is for individual atoms, but they're all molar mass. I will never use GFM, GMM, GAM. I will just use the word molar mass. Now, what I want from you is when you are taking molar masses from the periodic table, I want you to round it to 1 decimal place. Always 1 decimal place. That's what I want. That's what I want to see. Okay, so now we're going to start getting into more conversions. So we have the mole. 1 mole of something is 6.02 times 10 to the 23rd whatevers. So now we're going to look at how to convert between moles and mass and mole and volume. So you're going to get a couple more tools in your toolbox. We can use molar mass. So if I am given the grams of something, I can simply divide by the molar mass. 1 mole on top gives me the number of moles. And again, that's because molar mass is in terms of grams per mole. So pretty straightforward calculation there. We can also turn this around. So if I start with moles, I can divide by 1 mole, always 1 mole there on the bottom, and molar mass on top again, so the moles will cancel, giving us grams because, again, molar mass is in terms of grams. Volume, we can talk volume of a mole if we're talking a gas, but volume is a little trickier because for most things that aren't a gas, you have this density issues, you have spacing issues, so the volume of a mole of water is much less than the volume of a mole of sugar. But gases are much more predictable if we hold temperature and pressure constant. So what we do anytime we talk about the volume of a gas at this juncture, we're working at what's considered STP, or standard temperature and pressure. Consider that to be the always dealing with kind of condition. STP is defined as 0 degrees Celsius, the freezing point of water, and 101.3 kilopascals, which is a unit of pressure, or 1 atmosphere, which is also considered the unit of pressure. 1 atmosphere pressure, or 101.3 kilopascals, is the air pressure at sea level. So basically the pressure that we're at now. So keeping that in mind, we can say that the volume of 1 mole of a gas at STP is 22.4 liters. So we can say 1 mole of a gas equals 22.4 liters of a gas at STP. Now again, at STP is the only condition we'll be working with for the time being, so you don't have to worry about outside of STP. And this is actually what Avogadro figured out, that if two gases have the same temperature, same pressure, same volume, they'll have the same number of particles. So yeah, and that's why 1 mole was named after. Now, would 22.4 liters of one gas have the same mass as 22.4 liters of another gas at STP? Well, because they're both 22.4 liters, that tells us that there's 1 mole of each of them. So we really have to ask ourselves, does 1 mole of every gas have the same mass? In other words, does every gas have the same molar mass? And the answer to that, hopefully obviously, is no, because they all have different formulas. So if the molar masses are different, the mass of 1 mole of the gas will also be different. Now, where does this come in handy? Why do we do this? Really, it gives us another conversion. So we can say at STP, 1 mole equals 22.4 liters. Again, we have an equivalency. Anytime we have an equivalency, we have a conversion factor. So for example, let's say we want to find the number of moles in 33.6 liters of helium gas at STP. Well, what do we start with? We start with the thing that is not an equivalency. We start with 33.6 liters of helium gas. Now I'm going to cancel that out. So I need to find an equivalency that I can use to cancel out liters. Well, hey, 1 mole of any gas equals 22.4 liters. So I'm going to turn that into a ratio. Now we have to ask ourselves, who's on top, who's on bottom? Well, the 33.6 liters is what I start with, so I need to cancel out the liters, so I need the 22.4 liters on the bottom so I can cross-cancel, leaving me with the unit of moles. That's the unit I want, so I multiply across the top, 33.6 times 1, divide by 22.4, gives me 1.5 moles of helium. Finally, converting between the units, or the mole roadmap. So what you now have is you have a couple equivalencies all based on the mole. 22.4 liters equals 1 mole. Molar mass. So the molar mass of a substance, and you look at the atomic mass on the periodic table, is equal to 1 mole. 6.02 times 10 to the 23rd particles equals 1 mole. All of these are in terms of 1 mole. So what we can now do is we can chain together these conversions. Again, we will always start with what they give us. We will start with the thing that is not an equivalency, and we'll create a chain of ratios that will get us to where we want to be. Now, my biggest hint that I can give you is if you're not in moles, turn whatever you're given into moles. Moles by itself is not a super useful unit. What makes it useful is everything that's related to it. It's kind of the crossroads between a lot of this material. Okay, so now we're going to do some other calculations looking at percent composition and what that means. So the idea is that we've made a compound in the laboratory. We want to find out what it is. One of the first steps is to find the relative amounts of the elements within the compound. We call those relative amounts the percent composition. And what this is based upon is the mass of each element in the compound. So if we say that a compound is 25% carbon, that means that 25% of the mass of the compound comes from carbon. And there's going to be as many percent values of compound as there are elements. So for instance, if I'm looking at carbon dioxide, Carbon dioxide consists of carbon and oxygen. So we'd have 1% for carbon, 1% for oxygen. Here I have potassium dichromate, so we can see this is already done for us. You don't worry about where this comes from for now. We can see it's 26.5% potassium, 35.4% chromium, and 38.1% oxygen. So that would be the percent composition of potassium dichromate. And again, those percentages should add up to 100% if you did the process right. Now, the way that this works is the percentage is the number of grams of the element divided by the grams or the mass of the compound multiplied by 100%, which is a little bit wordy. So you can think of it in terms of this. So we take the grams of the element, which they would give us. So in this case, we're assuming that we're told you have 12 grams of carbon and 25 grams of the compound. Well, carbon mass up top, grams of the compound on the bottom, multiply by 100%. And when I say multiply by 100%, I mean multiply by 100, slap a percent sign on the end, call it good. So let's look at an example. An 8.20 gram piece of magnesium combines completely with 5.40 grams of oxygen to form a compound. What is the percent composition of this compound? So we're asking for percent composition. I remember from the previous slide, percent composition is mass of element divided by mass of compound, and I have to do that for as many elements as are present. How many elements do I have present? 2, magnesium and oxygen. So doing it with magnesium, the mass of the magnesium is 8.20 grams. But what's the mass of the compound? Are we told the mass of the compound? Well, sort of. They give us the mass of all the reactants, and conservation of mass tells us mass of reactants equals mass of product. So I add up the mass of my elements, gives me the mass of my compound, so the 13.60 is the mass of my compound. At this point, this becomes much simpler. So I'm going to divide the mass of each element by the mass of the compound, then multiply by 100%. So mass of magnesium is 8.20, mass of the compound is 13.6, times 100 gives me a percent composition of 60.3. I do the same thing with the oxygen. Oxygen mass was 5.40, mass of the compound still 13.6. Gives me a percent composition of 39.7. And now I use the fact that these should add up to 0 to double check my work. Sorry, not add up to 0, but add up to 100. So 60.3 plus 39.7 does add up to 100. So I did this right. Happy day. Okay, so now we're going to switch this around a little bit. We're going to find the percent composition of a compound we already know the formula of. So really, it's not much harder than just finding the molar mass. And again, where do we find the information for the molar mass? The periodic table, that's right. So what I do is I look up the molar mass of the compound. That tells me the mass of 1 mole of it. Then what I do is I kind of backtrack and I go, okay, for each element, how much mass did it contribute to the overall molar mass of the compound? And that's the mass of the element. Again, we have to use the subscripts here. Very, very important. So it's going to be a little bit clearer on the next slide. So for instance, we're going to calculate the percent composition of propane, C3H8. So first I find the molar mass of propane. So 3 moles of carbon is 36 grams because each mole of carbon is 12 grams. 8 moles of hydrogen is 8 grams. So that means the molar mass of propane is 44 grams. So that's the molar mass of the compound. That's what's going to go on the bottom. Now at the top is the mass of the element. And then what we use for that is the masses right here. So for the mass of carbon, I'm going to use 36. For the mass of hydrogen, I'm going to use 8. So mass of carbon, 36. Molar mass of the compound, 44. 36 divided by 44 times 100 is 81.8. Do the same thing for hydrogen. Get my answer. I double check by adding these together. They should add up to 100. They do. Oh, happy day. Finally, we're going to look at percent composition when we have a specific amount of a substance. So what we can use is we can use the percent composition to calculate how many grams of an element are in a specific amount of the compound. In other words, we're working backwards. To do this, we're going to multiply the mass of the compound that we're given by a conversion factor based upon the percent composition. Sounds harder than it really is. Okay, so I'm going to use propane. We're saying we have 82 grams of propane. We are told we have 82 grams of propane. That's not its molar mass. This is a specific amount of propane that we are told that we have. And we've already found its percent composition. We know it's 81.8% carbon, 18.2% hydrogen. Now, here's where the trick is. We want to think about what a percentage means. A percentage means how much there is out of 100. So when I say that it's 81.8% carbon, what that means is that for every 100 grams of propane, we have 81.8 grams of carbon. Also, for every 100 grams of propane, we have 18.2 grams of hydrogen. So whatever the percentage is, that's how many grams there are out of 100 grams of the compound. So we want to find the mass of the carbon, so we start again with the thing that we know, the 82 grams of propane. And again, you can put that over 1 if you want. Grams of propane, we want grams of propane to cancel, so 100 grams of propane on the bottom, 81.8 grams of carbon, that's what its percentage is. This number here will always be the percentage, and it gives us our answer. Pretty straightforward, nothing too tricky. Okay, so now we're going to look at empirical formulas. Empirical formulas are the next step in the process once we have the percent composition. So again, our kind of target here is we've made a compound in a laboratory. We want to know what it is. We found the percent composition. The next step is to find the empirical formula. And that's what we talk about there. What the empirical formula tells us, it's the lowest whole number ratio of the atoms of the elements in the compound. So for an ionic compound, it's the formula unit. It's exactly what's there. But for a molecular compound, it's the lowest ratio of all the atoms in the elements of the. For example, a compound could, let's say a compound has an empirical formula of CO. That's its empirical formula. Its true formula could be like C2O2, C6O6, C20O20, because it would all reduce down to CO. So another example, dinitrogen tetrahydride, its actual formula is N2H4. What would its empirical formula be? Well, 2 and 4 reduced down to 1 and 2, so it would have an empirical formula of NH2. Now, how do we calculate these empirical formulas now that we know what they are? So first we must know the percent composition. Then what we're going to do, we're going to do a trick. We're going to pretend, regardless of how much we actually have, we're going to pretend that we have 100 grams of the substance, because if we have 100 grams of the substance, this means whatever your percentage is, that's how many grams we can say that we have. So if something is 15% nitrogen, we can say we have 15 grams of nitrogen. So again, if something was 57% carbon, we could pretend that we have 57 grams of carbon. Just makes the math a lot easier. So I'm going to walk through this problem using this example. So what is the empirical formula of a compound that is 25.9% nitrogen and 74.1% oxygen? So first step is whatever those percentages are, that becomes how many grams we have. So we can say that we have 25.9 grams of nitrogen and 74.1 grams of oxygen, regardless of the amount we actually have. This is kind of pretending here. Now, what do I do with this? Well, you may remember from the previous sections, when you have something, what do you want to turn it into? Moles. How do we convert grams into moles? Molar mass. So I take the mass of the nitrogen, divide by the molar mass, moles on top, you can see grams of nitrogen cancel. Gives me moles of nitrogen. I do the exact same thing with the oxygen. Grams of oxygen cancel. leaves me with moles of oxygen. So we now have how many moles, relative number of moles of our elements that we have. So this is our current mole ratio. But we never want to see subscripts like that. Those are terrible subscripts. We like whole numbers. So what do? Divide everything, every number there, by the smallest number of moles you have. Looking at that, the smallest number of moles is 1.85, so I divide everything by 1.85. 1.85 divided by 1.85 is 1, so we have 1 mole of nitrogen. 4.63 divided by 1.85 is 2.5. So now we have a mole ratio of 1 nitrogen to 2.5 oxygens. Much, much, much better. Now, numbers to look for here. If our oxygen amount was like 2.9, we can just round that to 3. If it's like 2.06, round it to 2. But watch for things like near 0.25s, near 0.33s, near 0.5s, because those are things that we can do another sneaky thing with. What we can do is we can multiply everything by something that will give us a whole number, and it takes practice. So for example, that 2.5, we want to make that a whole number. What could I multiply everything by to give us a whole number? Well, 2.5 by 2 gives me a whole number. So I multiply everything by 2, so the 1 mole of nitrogen by 2 gives me 2. 2.5 moles of oxygen times 2 equals 5. Gives me a mole ratio of N2O5. That would be the empirical formula of this compound. So looking at an overview of this step by step, start with the percent composition, then determine the mass of each element in 100 grams. That is just simply taking whatever your percentage is and making it grams. Find the moles of each element. You do that by using the molar mass. In fact, you're going to be dividing by the molar mass in each of those cases. Then divide both mole ratios by the lowest number of moles. Sometimes you're done at this point, sometimes you're not. Finally, multiply everything by some number that will give us a whole number. Okay, we are almost done with this chapter. So now we're going to move on to the last step. So we've made a compound in the lab. We found its percent composition. We found its empirical formula. Now we're going to see how to transition from the empirical formula to the molecular formula. And again, the issue is that multiple compounds can have the same empirical formula. So like ethine and benzene both have an empirical formula of CH, very different compounds. Glucose, ethanoic acid, and methanol all have the empirical formula of CH2O. Glucose is blood sugar. We use that to live. Methanol is a terrible, terrible alcohol that will cause brain damage to you and burns invisibly. Nasty stuff. So we need to transition from the empirical formula to the molecular formula. Now the trick is that they will all have different molar masses. So if you have two compounds that have the same empirical formula, but they have a different molar mass, their molar masses will be a simple whole number multiple of what is called the EFM, or empirical formula mass. Now, what is the empirical formula mass? The empirical formula mass is simply the molar mass of the empirical formula. So you already have the empirical formula. Just add up the molar masses of all the elements that make it up. That's your empirical formula mass. So for instance, let's say a molecule's empirical formula mass is 12. We're told that. Its real molar mass could be 12, 24, 36, just a whole number multiple of that. If we know the empirical formula and the true molar mass of the compound, we can find its molecular formula. To do this, divide the molar mass by the empirical formula mass. If you get a fraction at this point, you did it backwards. So again, take the molar mass, which is given to you in the problem, and divide it by the empirical formula mass because you have the empirical formula. When you do that, that should give you a whole number. If you do not get a whole number out of this, double check your work. You probably made a mistake when doing the empirical formula mass. But if you do get a whole number out of there, now take that whole number and multiply all the subscripts by that same whole number. That will give you the actual molecular formula. So for instance, for each of these, we're going to calculate the molecular formula for these compounds. So we have the molar mass is 60, and the empirical formula is CH4N. We know the molar mass is 60. We know the empirical formula is CH4N. So I find the empirical formula mass first. 1 carbon, 4 hydrogens, 1 nitrogen equals 30 grams. So the empirical formula mass is 30. I now take the molar mass, or the GMM. So 60 divided by the empirical formula mass, 30, gives me the whole number 2. I can now multiply all of the subscripts by 2, giving me C2H8N2. Now, let's say a problem does not give you the empirical formula. Well, what do you need? Well, you need the percent composition, because if we have the percent composition, we can find the empirical formula. Or, what if they don't give you the percent composition? Well, then they have to give you the masses of your elements that you use to find the percent composition, that you use to find the empirical formula, that you use to find the molecular formula.